Good morning, everyone. Today we are going to discuss about the Proell Governor. In the last class, we have discussed about the Porter Governor. Proell Governor is also a gravity loaded or deadweight governor. The Proell Governor is different from the Porter Governor is the fly bars are connected to the spindle using and the extension arms. The systematic representation of the Proell Governor is shown in the figure, and here the fly bars are connected with the arms using these extension arms. These are the arms of the spindle, and this is the link of the spindle, and this is the extension arm. The polar gun also has center weight which increase the speed of rotation. The polar gunner function much more accurately than the watts or the porter governor and maintain a constant speed without any fluctuation. Then this is the figure 2 is the line diagram of the polar governor. Here again, the mass of the fly bars is more as compared to the mass of the links, arms, or the extended arms. Or we can say the mass of the arms, links, and extension arms is negligible as compared to fly bars. And the dead weight at the center of the spindle is capital W R is the radius of rotation of the governor, H is the height of the governor, T1 is the tension in the arm, and T2 is the tension in the link, alpha is the angle of inclination of arm to the vertical, and beta is the angle of inclination of the link to the vertical, and FC is the centrifugal force acting outward direction due to the rotation of the fly. Then, considering the equilibrium of forces on one half of the governor as shown in the figure 3, and considering the instantaneous center I lies on the intersection of the line PF produced and the line I from D, then draw the perpendicular to the spindle axis ID, and a perpendicular BM is drawn on the ID, and taking the moment about instantaneous center I, then the centrifugal force Fc into BM is equal to weight of the fly ball into I into M plus half of the dead center at the center into ID. We get the equation 1. Then the centrifugal force Fc is equal to weight of the fly ball into Im upon Bm plus half of the weight of the dead weight into Im plus Md divided by Bm. And here Im upon Bm is the tan alpha. Tan alpha is equal to either Im upon Bm or upon tan alpha is Im upon Bf, or we can say R by H, and the tan beta is equal to Md upon Bf. By multiplying the equation 1 by top and bottom by numerator and denominator Fm, then we get centrifugal force Fc is equal to Fm upon Bm into small mg into tan alpha plus capital Mg by 2 into tan alpha plus tan beta. And here the tan alpha is the ratio of the radius of governor to the height of the governor, and the ratio of the tan alpha upon tan beta is the Q. Then the centrifugal force is equal to Fm upon Bm multiplied by R by H into weight of the fly ball plus half of the weight of the center load into 1 plus Q is shown in the equation 2. So by solving the equation 2, we get the height of the governor h, that is h is equal to Fm upon Bm into gravitational force divided by omega square into mass of the fly ball plus half of the mass of the dead weight into 1 plus q. By substituting the value of the gravitational acceleration g is equal to 9.81 and the angular speed of the governor omega is equal to 2 pi n by 60, then we get the equation 3, that is the height of the governor h is equal to Fm upon Bm into small m plus capital M by 2 into 1 plus q into 895 divided by n square. When the length of the arm are equal to the length of the link, then the 10 alpha is equal to 10 beta, then q is equal to 1, or we get the equation number 4. When the loaded sleeve moves up and down the spindle, the friction force acts on it in direction opposite to that the motion of the sleeve. By considering the friction force, we get the equation number 5, that is the height of governor H is equal to Fm upon Bm into twice of the weight of the fly ball plus dead weight plus minus friction force into 1 plus q divided by twice of the dead weight multiplied by 895 upon n square. And here in the equation 5, plus sign is used when sleeve moves upward or governor speed increases, and the minus sign in the equation 5 is used when the governor moves downward or the governor speed decreases. So, to solve the equation 5, there are the three different cases. Case 1 is when the length of the link is equal to length of the arm, or we can say 10 alpha is equal to 10 beta, then q is equal to 1. Then the height of the governor h is equal to Fm upon Bm into the mg plus capital Mg plus minus f divided by the small mg multiplied by 895 divided by m square. The case 2, when the friction force is equal to 0, then the height of governor is Fm divided by Bm plus 2m plus m into 1 plus q divided by 2m into 95 divided by n square. And the case 3, when q is equal to 1 and there is a no friction force, then height of the governor is equal to Fm upon Bm into small m plus capital M upon m into 95 divided by n square. So here the difference between the Porter governor and Proell governor is the ratio of the Fm upon Bm. By adding this ratio Fm upon Bm, we have increased the sensitiveness of the governor. Then we have solved taken the problem. In a Proell governor, the mass of each bar is 8 kg and the mass of the sleeve is 120 kg. Each arm 180 mm long. The length of the extension of lower arm to which the bars are attached is 80 mm and the distance of pivot of the arm from axis of rotation is 30 mm and radius of rotation of the bar is 160 mm when the arms are inclined at 40 degree to the axis of rotation. Determine the equilibrium speed. Second, coefficient of insensitiveness if the friction of the mechanism is equal to 30 Newton. And third is the range of speed when governor is inoperative. So here weight of the fly ball small m is 8 kg and the capital M is 120 kg. The radius of the rotation of the ball r dash is 160 mm and the distance md is equal to mi, or we can say b is equal to c is equal to 180 into sine 40 degree, and that is 115.7 mm, and the r is equal to b plus 30 mm. 30 mm is the distance of the pivot of the arm from axis rotation. So R is equal to B plus 30, that is 145.7 mm. And the distance FM is equal to 180 plus cos 40, that is 137.9 mm. And the distance EF, that is R dash minus R, is 14.3 mm. And the distance BE, that is the root of BF square plus EF square, is 78.7 mm. So the distance BM is equal to E is equal to A plus B, that is 216.6 mm. So taking the moment about the instantaneous center I, central figure force into BM, or we can say central figure force into E, is equal to the mass of the flywheel into C plus R minus R dash plus half of the dead weight plus B plus C. By solving this equation, the angular speed omega is equal to 22.8 radian per second, or the n is equal to 217.7 rpm. Then considering the friction, we calculate the omega 1 and omega 2 maximum and minimum speeds respectively. For the omega 2, when the speed is reduced, then the friction force is minus 30. And in the second case, when we get the omega 1, when the speed is increased, then the friction force is positive. Here, omega n2 is equal to 251.1 rpm and N1 is equal to 220.3 rpm. So the coefficient of insensitiveness is 2.39%, and the range of speed N1 is 5.2 rpm. In the next class, we will discuss about the Hartner governor or spring-loaded governor.